All right, we are now going to spin things around both the X and the Y axis. Last year we did them on separate days. We're gonna do them today on the same day. This is the same idea if you've ever used a wheel in ceramics. That wheel is rotating. The axis happens to be vertical for that, but that rotation creates the symmetry around the axis. So you get this rounded thing and your hands can form the shape. We're doing the same thing. We're doing it around vertical and we're gonna do it around horizontal axes. Key to this is understanding the curve, which one's the top curve and which one's considered the bottom curve. This is the washer method. So this is what we're gonna get. So this is a horizontal axis. If you do any kind of woodworking and stuff too, you'll see people working on turning things to make like table legs and spindles and things that are formed this way. But everything is going to have a circular cross section or a donut cross section, okay? Either a disc or a donut or a washer, we call them that. So if it's a disc, it's solid. And if it's a washer or a donut or a bagel or whatever you want to call it, it's going to have a hole in the middle. So we're going to see it like this. This is something that would be have a hole in the middle that you could see all the way through. Like this bottom one down here, you can go all the way through that and come out the other side. There is a hole right there, so it's hollow, and so you can go all the way through. The top one, you can't go all the way through it because it is a solid point right there, so you couldn't actually pierce it all the way. But we practiced drawing last year, so like if you take this shape and you want to rotate it around the x-axis, you're going to do a reflection. So as best you can, you're going to draw the mirrored image reflection around the x-axis like that. And then do a kind of three-dimensional, so you'll have a circle here forming that edge, and then there's all these other circles, and all circles until you get to the end, and the back one has an open circle as well. But draw the reflection first, so you can see that reflected thing. And then have that outer edge. I like to maybe try and bold my outer edge a little bit so you can really see how that forms. Okay, so that's how we're going to be working these. So we just need to remember what the calculus is for this. So this is all based on round shapes. So it's all going to be pi r squared, but there's subtraction. So you're going to be having a pi r squared that forms the outer edge, the outer shell, or the outer wrap. And then you have a subtraction of a pi r squared that's going to be the inside piece that's going to get carved out, or that's not going to be there. So here's the subtraction. Here's how we learned how to set that up last year. Okay, so this is pi r squared. This f of x right here is your big radius, or your outer radius. Do anybody remember what alpha stood for? The axis, okay? Alpha stands for the axis of rotation. So a lot of times when we're rotating around the x-axis, the axis of rotation is 0. But if the axis is anywhere else, it could be a higher axis, it could be a lower axis. So we want to subtract that axis to account for the rotation. That whole thing is squared. So note that there's big parentheses here that group the outer radius minus the axis. That quantity is squared, and that is separate from the inner radius, which would be g of x, or sometimes we did capital R and lowercase r. And then you still have the axis of rotation, and that is separately squared from each other. So it's a separate subtraction. The subtraction is what carves out the inner part to make it hollow if it's going to be hollow. If it's solid, then that whole second part is going to be 0. That's what would make a solid piece, is if all of this turns out to be 0, then you have a solid piece. If it's not 0, then you're going to have a washer. You're going to have something that's got a center carved out of the middle. You could also take the pie. Since they both have a pie, what could you do with that pie? Yeah, you could pull it out to the front since they both have a pie as well. That would be another thing that you could do as you simplify that. Okay, so let's try this one. If I look at the original region, I'm going to draw the original region in red. Okay, so here's my original region. My outer edge is being formed by rad sine x. My lower region is being formed by the x-axis, and my rotation is also the x-axis. So we have our outer radius there, we have our inner, which is the lower bound, and we have our axis, which is the x-axis. So as we set up our volume will look like this. Parentheses, pi times the outer radius, which is rad sine x, minus 0, because 0 is the axis of rotation, that quantity squared. I'll clean that up in just a minute. I can simplify that. Then minus pi times the inner radius, or the lower radius, which happens to be 0. The axis also happens to be 0, that quantity squared. Finish out the whole parenthesis and put a dx. Now you'll get faster at this. I'm just showing you every tiny little step. You can easily simplify this, all right? I don't mind, so you don't need this part because it's going to be 0. This is a solid piece. When the lower boundary is the same as your axis of rotation, you'll have a solid piece. And the bounds are going to be 0 to pi. So then we'll have 0 to pi of pi times sine of x dx. And it turns out to be a pretty simple antiderivative to do. I can pull the pi out to the front and then have my negative cosine of x be my antiderivative going from 0 to pi. So I'm not going to finish that, but that's the setup on that. Does anybody have questions on that one? Okay. All right, this one doesn't come with a picture, so we're going to have to sketch it for ourselves. So we want the graph of 2x cos x and the x-axis. Bless you. Okay, the graph of 2x cos x and the x-axis. All right, so this graph starts at 2 here, and it looks like this. I don't expect you to know what that is. You'll be checking on your graphing calculator, okay? And we're going from -2 to +2. Ooh, that symmetry wasn't super great. And so the rotation of that is I try and draw a mirror image, kind of look like this. Okay, so kind of like that as we're rotating over the x-axis. Kind of reminds me of a pot or a vase turned on its side. But this is solid again because I'm rotating around the x-axis and the boundary is the x-axis. So my volume going from -2 to 2, lead with the parenthesis, and then pi times 2 plus x cos x minus 0, because 0 is the axis of rotation, squared. And then what turns out in this case to be 0 minus 0 again, axis squared. So we do end up having the solid piece because, again, the region and the axis are the same. The lower boundary of the region and the axis of rotation end up to be identical. So we're just going to practice setting these up and maybe cleaning them up. I could pull pi out to the outside, and all I'd be left with is 2 plus x cos x quantity squared dx. And you could run that through a Math 9 and have your volume of that solid that got generated by that rotation. Okay?
Start with pi in the front, or
Sure. Yeah. Okay. All right, here's one where we have two curves, but they're still rotated around the x-axis. So you want to be real clear about what's what. This drawing is a little bit deceptive because of the way the, like where the x squared is, they put it, and where the rad x is. But this one is going to be your upper. Okay, because in the region from 0 to 1, the rad x is the upper one. And then your lower is going to be the x squared. And when we rotate that around the x-axis, then we'll have a partially carved out piece in the middle, but it is solid right at the tip. The only solid part is actually the vertex of that. So our volume is going to be, okay, Gracie, we'll pull the pi out to start. This will be 0 to 1. We still need a double set of parentheses, though. So my first set of parentheses would be the upper, which is rad x, minus the axis of rotation, which is 0, and then that quantity is squared. So that'll form the circular path of the outer region, and then minus the parabola minus 0, that quantity squared, and then the whole thing dx. So as we clean this up in its most simplified form, we'll end up with x minus x to the 4th. So subtracting 0 and squaring each term. So squaring the square root and squaring the parabola. And then you'd run the antiderivative. That would be one you'd do by hand, right? So the previous one I'd let you run through a Math 9 because that antiderivative, it is possible. You would need integration by parts. So it's possible, but it takes too long. This one, you should be able to do it by hand. Okay, now let's do a different axis. So let's take 2 cos x and 1, but let's rotate it around the line, the horizontal line. Y is 4. Okay, so you should be able to get a sketch of this. All right, 2 cos x looks like this. So here's 2 cosine. 2 plus cosine, I mean. So it's the cosine graph. Nope, I only shifted it up 1. Take it back. It should be up here, 3. There's 2 cosine x. Okay. And then the line 1. So here's the line 1. So we're looking at this region right here. those intersection spots, when does cosine get to its lowest point?
Negative pi.
Okay, over here on negative pi, and then on the right side at positive pi. Okay, my axis of rotation is y equals 4. So what's unique about this axis of rotation? Where's its position? It's above it. So the axis of rotation is actually up here. That's where y equals 4 is. So if I do my symmetry, my rotation, my reflection, I didn't plan this very well at all, did I? Okay, I'm gonna have, it's gonna be up here. It's gonna be all the way up there. So the outer is being formed by which of the edges? The linear one, okay? So the outer is actually the lower one in this case. It's not just the higher one, but that's going to be forming the outer edge. And then the cosine one is forming the inner edge. But it's okay. Trust your subtraction. It will take care of the subtraction, and the square will take care of all of that. So my volume is going to be, okay, we'll pull pi out to the outside. We're going to go from negative pi to pi. And then trust it. So I'm going to have, my outer is the number 1. I subtract the axis of rotation, which is the value of 4. And then I square that. So trust the subtraction and trust the square. So no matter what, even though 1 minus 4 is a negative number, the square will take care of that, make it a positive number, which basically means the outer circle, the outer edge, is consistently radius 3. It's radius 3 the whole time. So that outer edge that's being formed, kind of making a barrel type shape, is consistently radius 3 the whole time. There's no change in that. Okay? Now the inner radius is flexing. The inner radius is starting out radius 3, and then it's shrinking and it's getting narrower, and then the radius is gonna widen up again. So then we have 2 plus cos x, also minus 4, and that would be squared. So there's your setup. So I'll have pi, I'll have 9, and then minus, and then cosine of x minus 2 quantity squared dx. So I'm combining the 2 and the subtract 4. I'm squaring the negative 3. The other thing you could do to simplify this a little bit is you could use symmetry. Instead of going from bounds that are negative pi to positive pi, you could go from 0 to pi and then double it, because you have pure symmetry here on both sides of the axis. So that, if you were working through this by hand, that might be helpful to you to change your bounds. You don't have to, if you're doing a Math 9, you don't have to simplify it. But if you were doing it by hand, I might suggest thinking about that. Okay, any questions on that so far? Yeah.
Why did you get 2 pi up front?
Because I just changed my lower bound from negative pi to 0. So I basically cut my region in half because of symmetry. So then I had to double the volume. So it's like I'm only going from this part just because I recognize there's symmetry on both sides. That's not a necessary step, but it's something you could do. And then double it. Okay, let's spin around the y-axis. The general principle is exactly the same. You have an outer, you have an inner. The subtraction of the axis of symmetry. Determine your outer by your inner the same way you would do area. I would go from right to left. So I would say, okay, look at approaching it. And as you approach it from right to left, the thing that you're going to approach first, that'll be your outer. And then if you keep going, the line or the function you would approach second would be your inner, if you're trying to figure that out. The axis of rotation is still subtracted. And then you're going on bounds C to D. Everything would be in terms of y. So instead of y equals something, all your functions should be x equals something. Your axis of rotation will be x equals something instead of y. So let's try one of those. So let's say you have a parabola. So right now, the parabola is y equals. But you're rotating it around a vertical. So you're going to need to change this into x equals something. And so as you change that into x equals something, you'll take this, it'll be plus or minus the square root of y equals x minus 2. So then x is going to be equal to 2 plus or minus the square root of y. You're going to need it that way. You draw it still in y equals x minus 2 quantity squared, but you're going to need the algebra to be in the other form so that you're all in y terms. So let's take a look at our picture here. If we have 0 on the x-axis, where is the parabola, where's the vertex of the parabola found? In what direction? 2 to the right. All right, so my parabola is found here, 2 to the right. So there's my parabola. I also want the line x, so that's 2. I want the line x is 1. And so my region is this, it's not really a triangle, but it's that little wedge piece right there. That is the region I will be rotating. So I'll use my notability to get rid of the extra stuff I don't really need. So there's my region. My axis of rotation is at the number 4. So here's my axis of rotation. So as I rotate that, the reflection is going to be out here. There's the reflected piece. So that's literally from 6 to 7. So it'll have a big, wide open. Something like that. Not my best work, but get the idea. So you'll need to establish, okay, what is my outer? What is forming the outer edge? And the outer edge is being formed by what was on the line, the number 1. So this is your outer edge. And then your inner edge is being formed by that section of the parabola. So as we set this up, we're going to take special care about making sure we are in y terms. So our volume will be pi times, I'll come back and do my bounds in just a second. The outer is the number 1 minus the axis of rotation, which is the number 4. So we have another axis that's going to be, radius that's going to be consistently 3. And then minus, now we need to describe the parabola. So as we got our parabola by itself, we said 2 plus or minus rad y. Now we can't leave it like that. We can't have a plus or a minus in the equation. We have to choose the plus or the minus. Don't leave both. So remember what the parabola used to look like. I erased this part and I erased this part. Which am I keeping the right side or the left side? I kept something on the left. If the parabola was split in half, I'm keeping the left side. That's the minus side. That's 2 minus rad y. And so go back to your integral and take out it's not going to be the addition. It's only going to be the subtraction because you're only taking half of the parabola, not both sides of the parabola. And then minus 4 for the axis of symmetry, or axis of rotation, and then that whole quantity dy, not dx. And now let's make sure our bounds are good. Be careful, the bounds are not 1 to 2. I know that's what I've got labeled on the x-axis, but we want to know what are the bounds along the y-axis. So it's not 1 to 2, it's 0 to something. Okay, it's 0 to 1 is where those things intersect. So on a multiple choice, that could be something that you watch out for, is that they have everything set up correctly, except you maybe would use the bounds 1 to 2 on the x-axis instead of the bounds 0 to 1 on the y-axis. So as we look at the whole thing, we're looking at 9 minus, and then we'll have negative rad y minus 2 quantity squared dy. And then depending on whether you were doing that by hand or doing it with a Math 9 will depend on how much more work you have. If you're by hand, you're going to have to FOIL it out so that you can take the antiderivative. If you were Math 9, you just run it through your Math 9 program.